Good morning. This is our 419 computable general equilibrium models. Today we continue discussing calibration of model parameters, and we're going to still use social accounting matrices. We're going to have different examples. At the end, we will discuss the issue of identification in terms of how it is relevant when we think of calibrating our model parameters. So let me share my whiteboard now and open a new page here. Okay. So once again, we have something like this. All right. So in the data, we have a social accounting matrix, okay, for a particular economy, right? So this matrix has rows and columns, and the transactions data is recorded in the social accounting matrix. All right. In the meantime, we have the model SAM. All right. Now, model SAM is also a matrix. Again, it's a square matrix. Once again, there are rows, there are columns, but this is the social accounting matrix originating from the model. For this reason, it depends on parameters. All right, so theta here. So theta is in some set. Okay, so this could be many. So theta could be theta 1 ... let's say theta r. Okay, so there could be many theta. So these are models structural parameters. Okay, now in calibration, we basically want to find theta that minimizes some distance between SAM data and SAM model. Okay, because basically we can choose different theta values, right? Different theta values to find a SAM model entry that corresponds to the same entry in SAM data. Okay, and when we do that, of course, in that part, we are using the theory and the solution. Okay, solution of the model. So now, if we look at the Cobb-Douglas utility function, for instance, right? We discussed this last week. So if you think about a very simple utility problem with two goods, right? So suppose that this utility function is like this. So alpha, well, let's say beta ln C1, 1 minus beta ln C2, right? Now, suppose that this consumer faces these prices and income is given like this. All right, so in this model, obviously beta is between 0 and 1, P1, P2, and income. So these are prices and income. These are positive and given, right? And if you solve this, obviously the solution is this, right? So a fraction beta of income is spent to first good, a fraction 1 minus beta of income is spent to second good, right? So from this in the theory, so you have the total amount of spending on good 1, right, which is beta W, and you have the total spending on good 2, which is 1 minus beta W. Okay. Now, obviously, then you have a particular information about your model parameter beta, right? Because beta should be equal to P1 C1 star divided by W, and 1 minus beta must be equal to P2 C2 star divided by W. All right. Now, if you think about this in a large economy, so there would be many different people, right, in this economy. So they all consume the first good and the second good, and they all have their incomes. Okay. And if their utility function is the same, okay, if beta is same for everybody, then you can typically aggregate these consumption expenditures, right? Because if this is C1H, if this is C2H, and this is WH, then you can find, you can write total spending, for instance, on first good in this way, right? And total spending on the second good in this way. Okay, and obviously these are also depend on betas, right? So if you write this, so beta goes out, right? So you can do that. So eventually, if you look at the model SAM, so this is your model SAM, right? I mean, if you now write the social accounting matrix, okay, you have the goods here. So let's say this is firm 1, this is firm 2, and then you have consumer 1, consumer 2, etc. Right? So that goes on. Firm 1, firm 2, consumer 1, consumer 2. Now, obviously, you know, part of the firm 1's revenue is originating from first consumer, another part originating from second consumer. The same is true for the second firm. And consumers, so here you have production factors, right? Consumers obtain some income. So here you have factor 1, factor 2. So consumers obtain some income from the ownership of these production factors, right? And then these factors, these production factors as accounts, so their income originates from firm 1 and firm 2, right? Now, so in the model now, model SAM, you have particular equations here, right? Not just numbers. These are equations that we just found, right? So these equations, right? So for instance, this is this is an equation that tells you something about the parameter beta. Okay. So then, of course, you're going to do the similar thing for the firm problem. Okay, I'm going to show you in a moment for the firm problem. When the firm production function, for instance, is called Douglas, then you're going to, again, find some relationship between factor prices and factor demands and the production function parameters. Then total payments to factor 1 and total payments to factor 2 and their ratio, for instance, in the Douglas case, will tell you something about these parameter values. Okay. So important notion here is, you know, to understand in the data, you have the numbers, all right? So there are rows, there are columns, and these are numerical values. And in the model SAM, you have particular equations that feature your structural parameters. Okay, so the idea is to recover these structural. So in the simplest case, for instance, we have directly the equations, right? So SAM data ij will be equal to SAM model ij theta. So you're going to solve this equation to find theta. Okay, so this is what we do when we look at the spending on the first good. Let's say this spending is equal to $80, okay, and the income is equal to $100. Then we understand that this parameter is equal to 0.8, right? So that's where we can use the solution directly to solve for beta. In some other models that are more complicated, we're gonna write, as I discussed last week, we're gonna write some sort of an algorithm, some sort of a numerical algorithm that minimizes a distance between model SAM and the data SAM. Okay. Now, what I want to do now is to show the firm problem. So calibration of production function parameters. Okay, so this is from your textbook. So first, let's look at the Cobb-Douglas case. Okay, so remember the problem faced by a firm is to choose, let's say, some x1 and x2 to minimize this cost function, right, subject to some target. Now here, we're gonna have mu x1 alpha, x2 1 minus alpha, and obviously the effective prices are positive. Mu is some positive parameter, and alpha is between 0 and 1. All right. Now, if you solve this problem, you of course realize that. So how do you solve this problem? You can set up the Lagrange, right? Typically, I formulate this as a maximization problem. So I put a minus here. So you can do it in the way you always use, but typically I use this. So there's this Lagrange multiplier, and then there's this constraint, right? So if you take the first of the conditions, eventually what you realize here is that if you call this function f, right? So you will have omega 1 plus lambda minus the derivative of f. So this is basically marginal productivity, right? Derivative of f with respect to x1. So this will be equal to 0. Of course, here we are assuming that these are positive. So we assume a okay. Here, actually, I have a sign problem. So this will be like this. Sorry about that. So this will be like mu x1 alpha, x2 1 minus alpha minus VA. So here, these will be positive, okay? Because I want to interpret lambda as a positive number, all right? But anyhow, so this is now formulated as a maximization problem. It's not really important. What is important here is that lambda will be equal to, so the marginal productivity, so this is omega 1 divided by the marginal productivity, okay? And this is omega 2 marginal productivity, okay? So if you do this, if you use this equation at the end, what you will find is this. So omega 1 divided by omega 2 will be equal to alpha x1 divided by 1 minus alpha x2, right? So this is the beauty of Cobb-Douglas production function, obviously, right? Mu basically disappears. Now, what is this? So this is your model-SEM relationship, but you should also realize this. Wait, I have a problem here. Once again, another typo. So this will be obviously x2, right? You should be alert because they should be inversely related with the factor price ratios, obviously, right? Now you realize the total spending by the firm on the first good divided by total spending on the second factor, sorry, not the good, so these are production factors, depends on this ratio of alpha to 1 minus alpha, all right? But in the SEM, you have basically these numbers, right? Total payments to factor 1 divided by total payments to factor 2. Okay? And let's say this number is, I don't know, let's say 2. All right, then you have some relationship between, so you basically know here what alpha should be, right? Using this equation, now alpha is equal to 2 minus 2 alpha, so 3 alpha is equal to 2. Your alpha is 2 divided by 3. Okay? So in the case of Cobb-Douglas production function, it's very simple, but there is also this mu, right? So remember, production function for the value added is expressed in this way. So we have to pay attention to this as well, and this is how we do it. So if you solve, if you remember the solution of the cost function, so it is like this in the Cobb-Douglas case. Alpha minus alpha minus 1 minus alpha, W1 alpha, W2 1 minus alpha times VA. Okay? So if you solve, if you remember our chapter 3 model, so if you solve that model, eventually you're gonna find that. All right? So total cost given the value added. Okay, so how do you know that? So you put x1 and x2 star into this. All right, so this is your cost function to x2. So if you put these optimal values, of course, depend on factor prices and the value added, right? So W2, X2, omega 1, omega 2, VA, right? So if you solve this equation, you find that. Now, careful, as I said last week, we normalize prices to 1 in calibration by changing the measurement units, right? So we change the measurement units of any particular physical good in the economy. So here there are production factors, such that we always express prices as equal to 1. So when we look at the SEM data, when we look at the social accounting metrics in the economy, we always interpret these entries, these numbers as quantities. Okay? So once we do that, this equation looks like this. C omega VA equals 1 divided by mu alpha to the minus alpha, 1 minus alpha to the minus 1 minus alpha times VA, right? Now, remember that this is the price of value added, right? This is the price of value added. And it is also a price. So what we want to do, we want to do also equate this to 1. How do we do that? Well, again, we change the measurement units, right? Because in the production function, remember your production function. Let me use a different color. So value added is expressed in this way. So this is a free parameter then, right? It depends on how do I measure the production, how do I measure these inputs, and how do I convert the measurement unit of this composite to the measurement unit of value added. So I can actually choose it to normalize this to 1, okay? So to be more specific, of course, this was the price of value added. And this was depending on that. But then at the end, we wanted to 1, okay? And then we have this result, okay? So what does this tell me? Well, remember that alpha is 2/3, right? From the other equation. So alpha is 2/3. Then mu is basically equal to alpha to the minus alpha, 1 minus alpha to the minus 1 minus alpha. So I calibrate both parameters, both alpha and mu, right, for the production function. So what matters here is that you have to use the price normalizations, okay? Because in the social accounting matrix, you want to interpret these entries, these numbers as quantities, okay? So this whole thing becomes equal to what? Becomes equal to value added itself, right? Because this part becomes 1. Okay? So that's for the case of that's the case for Cobb-Douglas production function. Now at the very end, I will show you in the CES production function. Remember the CES production function. So it is like this. A CES production function is like alpha 1 x1 row, alpha 2 x2 row to the power of 1 over rho. So here rho is the parameter that takes values from minus infinity to 1, and that determines the elasticity of substitution. So elasticity of substitution here is sigma, and it is equal to 1 over 1 minus rho. So if rho is equal to minus infinity, this elasticity, so if rho goes to minus infinity, then elasticity goes to 0, right? So there's no substitution. If rho goes to 1, then elasticity goes to positive infinity. So it is maximum elasticity. If rho goes to 0, then sigma goes to 1, and this is called that. So this is Leontief production function. This is linear production function, and this is Cobb-Douglas production function. So I will show you that we cannot identify all parameters in the case of CES. So this is CES production function, and here identification is kind of problematic, and I will show you this. Okay, so we have less than a minute. Let's take a break. It is 9:40 now. Let's meet at 9:55. Okay. 9:55. That's okay for everybody?
Okay.
Yes.
All right, okay. I'm ending the session now.